So we're in section 9.2. And yesterday we learned about chords and the arcs and how we measure arcs and how we find the length of arcs. Now we're going to talk about a couple of lines that have something to do with circles. So we'll start out by defining a secant and defining a tangent, and then we'll talk about the relationships that we're interested in. So a secant. A secant is a line that intersects a circle in 2 points. And our picture for a secant, here's our circle and our line. We trained it to this. So there's a secant line. And so our secant line intersects the circle in 2 points. And from yesterday, what do we call this segment that's between these 2 points that's inside the circle? What is that segment? What's the segment inside a circle that has its endpoints on the circle? Chord, there we go. So this is a chord. So a secant is a line, and inside the circle, the secant, between where it intersects the circle is a chord. So this is our secant line. So that's one of the lines that we're interested in today. The second is a tangent. A tangent line intersects a circle in exactly 1 point. So our picture for a tangent line would be, here's our circle, and we'll do our tangent line in blue. So that would be our tangent line. And the point that it intersects right here, we call it the tangent point or the point of tangency. So this is a tangent line.
So there could be like millions of those on one circle.
Right. At any point around the circle, we could have a tangent point.
Like that.
So that's a tangent line. And this is the tangent point or the point of tangency. And if you go on to study more math, if you study calculus, tangent lines are one of the main things that you study in calculus. Tangent lines are really important. Because what happens is on a curve, if you have some kind of curve, where the curve is at a maximum or a minimum, the tangent line is horizontal. So that tells you something. If you figure out when the tangent line is horizontal, you know you have a maximum or minimum. And at other points on the curve, the tangent line tells you the slope of the curve right at that point. So it tells you how the curve is changing. So if the curve is describing something that you're interested in, the tangent line tells you how it's changing right at that point. So tangents are a very important idea as you go on in math. But today we're just talking about tangent lines to circles. Secant and tangent come from Latin. Tangent comes from to touch, and secant comes from to cut. So a tangent line just touches the curve. The secant line cuts through the circle. I thought that was kind of interesting. Now, what we're interested in with the secants and the tangents is how they're related to the other parts of the circle that we've already talked about. So yesterday we talked about radiuses and chords. So the first thing we're going to look at, and I have a little demonstration to kind of get us thinking about how it works, is how is a tangent line related to, or how is a secant line related to the radius of a circle. So let me pull up that little demonstration. So what we have here is a circle. Let me make it a little smaller. And segment AB is a radius, and line BC is a secant line right now. So it's intersecting the circle in 2 points. And what we're measuring up here is this angle ABC, the angle between the radius and the secant line. So as the point moves around the circle, this angle changes. What we're interested in is what happens when point C moves closer and closer and closer and closer to point B, so that this secant line turns into a tangent line, so that this point is the only point where the line is touching, and we want to figure out what that angle is going to turn into. So anybody have a guess? So we have a guess of 90. When point C and point B are right on top of each other, when this secant line turns into a tangent line, we think that maybe this angle would be 90 degrees. So here we go, we're getting closer. So that angle's getting bigger and bigger and bigger. Oh, I went past. There we go. So that's pretty close. It's hard to get it right at 90 degrees. So here point B and point C are right on top of each other, and the angle between the radius and the tangent line is about as close to 90 degrees as I can get it. So let me pull this around, and let's do, we can make a different, I can do a different radius. It doesn't matter where my radius is. So let's bring this around. So B and C are right on top of each other again. So that's about as close as I can get it there. So when B and C are right on top of each other, so when this secant turns into a tangent, the radius and the tangent line are perpendicular. They make a 90-degree angle. So let's go back to our notes. This is our theorem. So we kind of did a demonstration. It turns out that this is our theorem, for one of our theorems for this segment. This is the tangent theorem. And the tangent theorem tells us that if a line is tangent to a circle, then the line is perpendicular to the radius at the tangent point. And our drawing looks just like the drawing on our demo. So our circle, we'll draw a radius. Whoops, don't want the arrows on there. So there's our radius, and we'll draw a tangent line. We'll do the tangent line in blue. So there's my tangent line, and this is a 90-degree angle. And that's a radius. That's my tangent line. And this is the tangent point. So that's what the tangent theorem tells us. So we can add this to our little tricks that we learned about circles from yesterday. A couple of things that we talked about yesterday that I said you need to remember is that if you're not sure how to solve a problem with a circle, draw in another radius. And we also remember that all radii in the circle have the same length. So here's another trick, that the tangent line is perpendicular to the radius where they meet. So we'll use that to solve problems with circles also. It turns out that the converse of the tangent theorem is true also. Do we remember how to make a converse if we have an if-then statement? What do we do to make a converse? Anybody remember? No ideas on converses? Converse, we switch the order of the if and the then. So our converse would say, if a line is perpendicular to the radius at a tangent point, then the line is tangent to the circle. So the converse of the tangent theorem is also true. So it's the same picture. I'm just going to write the converse of the tangent theorem. So our converse tells us that if a line is perpendicular to a radius, then it is tangent to the circle. And it's tangent, so we're saying it's perpendicular to the radius at the end point, at the radius's end point. So I'm going to erase that and add that in, just so we make sure we know what we're talking about. So if it's perpendicular to a radius at its end point on the circle, then it is tangent to the circle. And our drawing looks just like the drawing that we had before. It's just saying that if we know that the line's perpendicular to the radius where they meet on the circle, then it's tangent to the circle. And the other way, the tangent theorem, the converse of this one, says if it's tangent to the circle, then it is perpendicular to the radius. So questions on the tangent theorem. All right, the next thing we're interested in is how a radius and a chord are related. So what we want to do is look at what happens when we have a radius and a chord inside the circle. How are they related? What can we figure out about those? So I have a demo for that one also. Let me close this. So here's this demo, and we have a circle again, and segment AB is a radius of the circle, and segment DC is a chord. Its endpoints are on the circle. What we're measuring here angle DEA is this angle here, the angle between the radius and the chord. And DE is the length of this part of the chord from the circle to point E. And EC is measuring the distance from the radius to this part of the circle, so this part of the chord. What we're interested in this demo is to see what happens when the chord and the radius are perpendicular. What happens to these two distances? So as I bring point D around and this angle gets closer to 90 degrees, what happens to these two distances? Anybody want to guess about that one? So we're looking at this distance from D to E and the distance from E to C. So Haley says she thinks they're going to be the same. So when we get to 90 degrees, we're almost there, almost there. So what happened? They're the same. So when the chord and the radius are perpendicular, the length from here to here and here to here is the same. So it cuts the chord in half. Let's put the radius in a different place, and let's make the chord, put the chord in a different place, and we'll bring that around to 90 degrees and see if it's the same, see if it changes. That's about as close as I can get. So they're the same again. I put the radius in a different place, put the chord in a different place. We can bring the chord so it's shorter, so the lengths are shorter. So they're pretty close. I'm not sure if I can get it closer than, oh, there we go. There we go. So when we have a 90-degree angle here, this length and this length are the same. It cuts the chord, the radius cuts the chord in half. So do we remember what special geometry word we used when something cut something else in half? How many pieces is, what is it? Bisect. So the radius bisects the chord. So that's going to be our theorem. This is our radius and chord theorem. So let's go back to our notes. And we have the radius and chord theorem now. The radius and chord theorem tells us that if a line is a radius that is perpendicular to a chord, bisects that chord. And remember, bisect means cut in half. And our picture for this looks like our picture for the demo. So here's our circle. Let me mark the center. And we'll draw in a radius. There's our radius, and we'll draw the chord in blue. And we'll say that this is a 90-degree angle. And we'll label some points here. We'll call this point P, point R, point A, point X, and point B. So this tells us that AX and XB are the same. So PR, segment PR, bisects segment AB. And the other way of saying that is AX equals XB. Those lengths are the same. Any ideas how we might go about proving the radius and chord theorem? What was our hint from yesterday? If we don't know what to do. Draw in what? What part of the circle do we know is always the same no matter where it is? The radius. So we're going to draw in a radius. So here's my radius. I'll do my radius in green. I'm going to draw in 2 radii. We know those are the same, so those are congruent. So in these 2 triangles, what can we say about this segment that they share? It's congruent to itself, right? So now we have a right triangle with a hypotenuse and leg congruent. So what can we say about the 2 triangles? Triangles are congruent by hypotenuse leg. So that means all the parts of the triangle are the same. So that tells us that AX and XB are the same. So just like we did yesterday, to solve our problem with the circle, we drew in 2 more radii. We knew that they were always the same length, so they're congruent. And a problem with a circle turns into problems with triangles. So just like I said yesterday, problems with circles often turn into problems about triangles. Any questions on radius and chord theorem? This one is going to come up a lot as we work through chapter 9. All right, let's look at one example. Here's a type of problem that you might have to solve using the radius and chord theorem. So here's our picture. We'll draw in the center and a radius. And a chord. And this is a 90-degree angle. And we're going to call this point P, point R, point A, X, and B again. And this length is 6, and the length of AB is 10. We want to find the length of the radius. So all we know is that the length of AB is 10, and this little piece of the radius is 6. We want to find the length of the whole radius. Anybody have an idea of how we might do it? So what was our hint from yesterday? Draw in another radius. So let's draw in another radius. Draw it in green. So there's my radius. What kind of triangle do I have here? A right triangle. I know one side. If I could figure out this side right here, I could use a Pythagorean theorem, right? This whole length from A to B is 10. It's 5 because the radius is perpendicular to the chord, so the radius cuts the chord in half. So that length is 5. This is my radius. So now I can use the Pythagorean theorem. R squared equals 6 squared plus 5 squared. The radius is the hypotenuse of that triangle. So R squared equals 36 plus 25 r squared equals 61, and r equals the square root of 61, which is about 7.81 units. So we weren't sure what to do. We drew in a radius, and our problem with a circle turns into a problem with a triangle. Questions? All right.